Hello everyone. So in these lectures now we will move on to study fermions. So our goal is to study fermions, and the reason for studying fermions is that the fermions are extremely important. I mean, for example, the matter is made up of electron, proton and neutron. They are all fermionic particles. Okay, so this is the in order to understand our real world, fermions are very important object. So before we move on to the details of the fermion, let's first do some mathematical aspects, and these mathematical aspects is known as Spinor representations. Okay, so in the previous lecture we have seen that, so we have already discussed, we have already discussed the Lorentz group, and the Lorentz group is in 3 plus 1 dimension. This is just the there is a group, it just decomposes into product of two SU2s. Okay, this indices left and right is just a convention, there is no objective meaning of them. And we in from the quantum mechanics course we already know representations of SU2s. Okay, these are the angular momentum representations. Okay. Now in this lecture we will focus on in a very particular representation of this Lorentz group. So this we will focus on so you probably remember that the representation of this are denoted by two integers a comma b, where a determines the Casimir of SU2 left and b determines the Casimir of SU2 right. So in this lecture we will focus on two particular representations. One is called half comma 0. So this is a two-dimensional representation. And it is often called left-handed spinor. Left-handed spinor. So the name spinor, this name is for this particular representations. Okay. So this two-dimensional this representation is denoted, let's say, by lambda alpha, where alpha takes value 1 and 2. Okay. Often this is also denoted as this angle bracket notation. In modern high energy physics, these two things are same thing. Okay. Now, given two such things, so firstly, so invariant tensor of SU2 is epsilon alpha beta. Okay, so we can use this to basically we can use this to also define dot product. So for example, this object is SU2 invariant. Okay, so it is roughly like the dot product, but now for SU2 groups, not for Lorentz group. here also we will introduce a bit of a notation. So first we define, so introducing notation. So first we define lambda alpha, which is same as lambda upper alpha, which is same as epsilon alpha beta lambda beta. Okay, so these we can use to raise and lower indices. Okay, and then in that case this object okay, so this is the thing, this is the way we denote these things. So this is a very quick introduction to what do we mean by left-handed spinors. Again, we repeat, it's a two-dimensional representation, so it has two components, two complex components, and the invariant object that you can write down is this thing. Similarly, we can also define something called right-handed spinor. Which is simply the representation 0, half. Okay. So, so this also has two components. So this notation means this is invariant two-dimensional representation of SU2 right. So these representations we often denoted as, so we use it as tilde, and we use the index alpha dot to make it different from the index of SU2 left. So again, alpha dot takes value 1, 2. This thing is same as in this case. Again, we want it to be distinct from this left-handed spinor, so we use it angle bracket. Sorry, for right-handed spinners. And square bracket for left-handed spinners. Okay. In the same way, here also there is a dot product. So the same thing is that we can also define alpha dot lower index which is same as lambda tilde alpha dot. This is same as epsilon alpha dot beta dot lambda tilde beta dot. Okay, and the invariant dot product lambda 1 alpha dot lambda 2 alpha dot. Okay, so this is the invariant dot product that we defined for SU2 let. So this is also, as we said, these are the two components. So this concludes our very brief discussion of left-handed and right-handed spinners, and what do we mean by that? I mean, what we mean by left-handed spinner and what is we mean by right-handed spinner. So essentially, the spinners are smallest non-trivial representation the Lorentz group. Okay, so technically speaking, this is called smallest non-trivial representation of the spin group. This is not a Lorentz group. Okay, so let me elaborate on that. So you know that for fermions, the fermions do not for fermions. For spinners, 360-degree rotation is not an identity. Okay, 720-degree rotation is. Okay, given this means that, so this is like, so this is called, so this thing is called, so spin group is a double cover of Lorentz group. This means that for every element of, let's do the opposite, for two elements of the spin group, maps to one element of Lorentz group. Okay, so that's why it's called double cover, because it has double, basically roughly speaking, it has double the number of elements than the number of elements of the Lorentz group. Okay, and that's why the spinors, this fermions, these are actually technically speaking representation of the spin group, and that's why these are called spinors. Okay, now let us briefly discuss the action of the discrete symmetries. Okay, so we already discussed that under parity, this we have already discussed. Then under parity, in general, A comma B representation goes to B comma A. So this means that if I start from left-handed spinners, this goes to right-handed spinners. Okay, so the smallest representation, the smallest spinor representation or smallest fermionic representations, whatever you want to call it, they are not parity invariant. Okay, in order to have parity invariant, you need to have both of them. Similarly, under charge conjugation, okay, let me do the time reversal first. This is for parity. Under time reversal, the spinners, the representation, the left-handed remain the left-handed, and the right-handed remain the right-handed. Okay. Now let's do charge conjugation. So this is time reversal. Under charge conjugation, again A comma B goes to B comma A, which essentially means under charge conjugation, this again left-handed spinners goes to right-handed spinners and right-handed spinners goes to left-handed spinners. Okay, so this actually explains, you see that P or C is separately not, so this is charge conjugation. So left-handed or right-handed actually. Spinners are not invariant under C or P, but they are invariant under CP. Okay, and later we will see that even if the spinners are invariant, when you put interaction, the only symmetry, only set of discrete symmetry you will expect to be symmetry of your theory is CPT. Neither C nor P nor T, not any two combination of them, CP, PT, CT. None of them are actually preserved by interactions, but the only set that is preserved are the CPT symmetries. Okay. So this is a CPT theorem actually, it's a CPT theorem. any 3 plus one dimensional Lorentz invariant QFT must have CPT symmetry. Okay, the statement is that as long as the theory is Lorentz invariant, there is no way you can break the CPT symmetry. It has to be the symmetry of your theory. Great. Let's now discuss complex conjugation. So under complex conjugation, what happens is that under complex conjugation, the two SU2s flip, right? Again, we discussed this when we were discussing the Lorentz group. They flip under complex conjugation, which means under complex conjugation, left-handed spinner goes to right-handed spinner and right-handed spinner goes to left-handed spinner. This is an important property of this spinor representation, that under complex conjugation they flip. So which means that under complex conjugation, lambda alpha goes to this will be very important when we try to construct the action, because finally the action should be real. Whenever we try to construct an action, the action should be Hermitian, right? And that in order to get that property, we need to make sure that this complex conjugation property will become very important. So this will play an important role in ensuring the action is real. Okay, so this is the complex conjugation properties. Last not the least thing will be actually the discussion of the sigma matrices. So let's discuss. So consider the product of two representations. Consider the product of product. So, okay, then from addition of angular momentum for the individual SU2s, from the addition of angular momentum rule, that this will be same as half comma half. Okay, this physically means if so, you know that this is product of, so this is left-handed spinner. This is right-handed spinners. And this half comma half we already again discussed in the representation of the Lorentz group. This is the vector. So this essentially means that if we take product of two spinors, one left-handed and one left right-handed, then it is same as Lorentz vector. Follows from addition of angular moment. Okay. Now question is that it is same as, but then if it's addition of angular momentum, we have to say what are the Clebsch-Gordon coefficients, right? And these Clebsch-Gordon coefficients these are called sigma matrices. Okay, for example, take sigma mu alpha alpha dot. So this is as a matrix, this is same as I times the Pauli matrices. Similarly, there is also something called sigma bar mu alpha dot alpha, and this is same as identity minus sigma is. And then we can see that if I take now lambda 1 alpha sigma mu alpha dot lambda 2 tilde alpha dot, this thing is a Lorentz vector. Let's call it V mu. Okay, so you can see that this takes a left-handed spinor and a right-handed spinor, and map it to sigma matrix and map it to a Lorentz vector. Okay, so these are like that's why we calling them Clebsch-Gordon coefficients. So this is basically takes a thing sigma matrix two spinors and map it to a Lorentz vector. So let's actually use our notation. So this thing in our angle and square bracket notation, this thing simply becomes square bracket lambda 1 sigma mu angle bracket lambda 2. Similarly, lambda 2 tilde. Similarly, one can also define lambda 2 tilde angle bracket sigma bar mu, sigma bar, remember this is sigma bar lambda 1, and this is same as lambda 2 tilde alpha dot sigma bar alpha dot alpha lambda 1 alpha. Okay, so this is the sigma matrix properties. It's very important to remember. So important properties that you can show. One is lambda 1 tilde sigma bar mu lambda 2 angle bracket square bracket is same as lambda 2 square bracket sigma mu lambda 1 tilde angle bracket. Okay. Second is that Hermitian property. So let's take lambda 2 sigma mu lambda lambda 1 sigma mu lambda 2 tilde. If I take its Hermitian conjugate, this becomes lambda 2 sigma mu lambda 1 tilde. This is consistent because we know that the angle brackets goes to square bracket and the square bracket go to angle bracket under complex conjugation. This is basically saying that the left-handed spinor go to right-handed spinor and the right-handed spinor go to left-handed spinor under complex conjugation. And there is another very important identity which is called Fier's identity. Which is lambda 1 tilde sigma bar mu lambda 2 square bracket and then lambda 3 tilde sigma bar lower mu lambda 4. This is same as 2 times the dot product of lambda 1 lambda 3, the two right-handed spinors, and then the dot product of lambda 2 and lambda 4. Okay, all these identities can be shown and you can find it in any standard quantum field theory book. But if you have to deal with fermions, they will become extremely important. So this concludes our discussion of spinors and the spinor representations. In the next class, we will see that how to use this to construct the action of the fermions and how to then we will proceed and see how to quantize them.